Hi guys, welcome back to my channel. Today we're going to be looking at static particles. So when we have a particle that has two or more forces acting on it, it can appear to be stable if those forces are acting in equilibrium. So equilibrium is a steady state where all forces are balanced, and that's when the vector sum of all the forces acting on the particle is zero, and therefore the acceleration of that particle is going to be zero as well. So let's say we had two forces that are acting on a particular particle or a particular object. If these are linear forces, then they would act in opposition to each other. So we can see this here from the sum of F1 and F2 equals to 0. So that means that F1 and F2 are equal but opposite directions. So what happens when a particle is acted upon by three forces? Well, the net movement of that is also going to be 0. So for example, a particle has three forces acting upon it at its equilibrium. So if F1, F2, and F3 are found at 3i minus 4j, xi plus 7j, and 6i plus yj respectively, determine the values of x and y. All right, let's start off with our formula. So we know that if we were to add up all of these forces, and these are vector forces, so I'm going to put the tilde underneath, then that's going to be equal to 0. So that means that 3i, so substituting in our values now, 3i take 4j plus xi plus 7j plus 6i plus yj are all going to be equal to 0. So what we can do, we can go ahead and we can equate all of the horizontal components and we can equate all of the vertical components. So let's equate the horizontal components first. So if I have 3 plus x plus 6, that's going to be equal to 0. So 3 and 6 make 9, so therefore x is going to be equal to negative 9. Let's equate our vertical components now. So negative 4 plus 7 plus y is equal to 0. Negative 4 and 7 is equal to 3. Therefore, y must be equal to negative 3. Okay, so let's go ahead now and let's just rewrite our three vectors. So we've got f1, which we already knew was equal to 3i minus 4j. We have our second vector, f2. And we now know that our value for x was equal to negative 9 plus 7j. And then lastly, our third vector is going to be equal to 6i minus 3j. All right, so in this case, we can see that the three concurrent forces can be represented, and we can do this using a closed triangle. So this is really important to note that when we're doing these, it's really, really important to have these going from tail to head, tail to head, tail to head. If we have head to head, then we would actually be calculating, well, potentially the area, or potentially we would be calculating the resultant force. And that's not what we're trying to do here. So just be aware of that. So what we're going to do is we are going to look at this example here. So a particle is in equilibrium and is acted upon by three forces. So one force acts horizontally and has a magnitude of 7 newtons. Another force acts at right angles to this force and has a magnitude of 8 newtons. Determine the third force. So I find with problems like this, it's most useful to draw a diagram first, and then we can go ahead and find the length and the angle that we need. So let's do this. So first piece of information that we know, that one force is acting horizontally with a magnitude of 7 and one is at right angles and has a magnitude of 8. So if I was going to draw my graph here, I've got one vector that is horizontal and that is going to have a magnitude of 7. So this point here is going to be at 7, 0. We also have another vector that's operating at right angles to this. And that has a magnitude of 8, so this is going to be at 0, 8. Lastly, we have this third force, and I don't exactly know where this third force is just yet. I know that this is going to come down off this angle here, and I know that when I add these three vectors together, it's going to be equal to 0. So there's a couple of different ways that we could do this. The first way that we can do this is by making our triangle. So we've got to make our head to tail, head to tail, head to tail triangle. So I'm going to leave this value here at 7. So this is my my first force here. Then I'm going to move this down. So this was my second force here, and that has a magnitude of 8. And then this last force, this force that we don't know yet, that's going to move to meet the two corners. And you can see that this is going from tail to head, tail to head, tail to head. So we've got to work out this third force. So we need to work out the angle, and we also need to work out the magnitude of this force. All right, so since this is going to be a right angled triangle, as the question stated that these were at right angles to each other, this is going to be really simple because we can just use Pythagoras' theorem to find the length of this third side. Using Pythagoras' theorem, we can see that the magnitude of this force is going to be about 10.63 newtons. And again, because this is a right angled triangle, we can use an inverse tan function to find the value of our angle. Now that I have my angle, I'm going to actually express this as I would express a normal vector. So rather than going around this way, that's going to be outside of our principal argument. So I'm actually going to go 180, take away the angle, and then that will be within that neg 180 to positive 180 degrees, so inside the principal argument. So let's do that now. So we have an angle of 131.19 degrees going clockwise, or negative 131.19 degrees, if we were to express this using our normal vector notation. Okay, that was a fairly simple example. So let's go ahead and do a trickier example now. A particle is in equilibrium, so that means that the sum of the forces is going to be equal to 0. And it's acted upon by 3 forces. The first force acts horizontally and has a magnitude of F newtons. So if I start to draw this, we've got one here with a magnitude of F newtons. A second force, and when we draw this, we're going to draw this from the origin, has a magnitude of 2F and acts at 45 degrees with the first force. And we need to determine the value of the third force. So there's one of those two ways that we can do that. We can do that by using the sum of the vectors, as we've done previously, or we could do this by resolving the forces into its x and y components. So let's go ahead and let's solve this by using sum of the vectors first. All right, so I've gone ahead and I've redrawn my diagram. Now with this one, I've moved my forces. So this was my initial force here, right? I've moved this 2F force to about here. So that's the force we can see here. And so this third force is going to end up making the third edge of this particular triangle. Okay, so we can see pretty clearly that this is not going to be a right angled triangle, so we're not going to be able to use Pythagoras' theorem to solve. However, I do know the length of 2 of my sides, so I know this length here F, and I know this length here 2F. I also know this angle in here. So I'm going to use the cosine rule to determine the length of this third vector here. So substituting the values I know into my cosine formula, the length of this third side here, or the magnitude, is going to be equal to F multiplied by root 5 plus 2 root 2. And this has a decimal answer of approximately 2.8 F. Okay, so let's go ahead now. Now that we have the 3 sides and we have one of our angles, we want to compute this angle in here. So that's actually going to be equivalent to this angle in here because we can use our Z rule, and therefore that's going to be the same angle. All right, so now that we have our 3 sides and one angle, we can use our sine rule to solve for this last angle. Substituting the values I know into my sine rule, I get an angle of about 30.36 degrees. So if we go back up to my diagram now, this is going to be this angle in here, so 30.36 degrees. And again, if I go past this point here, this is going past my principal argument, past positive 180 degrees. So I'm going to actually work backwards here. So this is actually going to be equal to 149.64 degrees, and again that is going to be in the clockwise direction. The other way that we can express this would be as negative 149.64. Okay, so that's how we've used the sum of our vector forces. How would we actually go about doing this using the resolutes? So let's resolve the forces into their components by using our r cos theta and r sin theta rule, and then let's see if we can determine the value of the third force that way. So using my x is equal to r cos theta and y is equal to r sine theta formulas, I've been able to determine the vector resolutes of f and 2f here, or sorry, I should say f1 and f2. So now that I know this, how can I use this information to calculate the third vector? Well, we already know that the sum of the three vectors is going to be equal to 0. So let's substitute in the information. So given this information, to find f3 on its own, what I'm going to do is I'm going to subtract each of these from this side. Now that I have the x and the y component for my third vector, I can go ahead and find the magnitude. And again, we can just use Pythagoras' theorem to find this magnitude. So using our vectors and using Pythagoras' theorem, we're actually able to show that the magnitude of the vector is going to be the same. So now that we know this, let's go ahead and calculate our angle. So using our inverse tan y over x is equal to theta rule, we're actually able to show that the angle indeed was the same as before. And we do have to keep in mind that with that vector, because that is coming down here, and we do want to remain within our principal argument from negative 180 degrees all the way around to positive 180 degrees, we're going to do 180 minus our angle, and that was going to give us negative 149 point, what was it from before? All right, so our final angle was negative 149.64 degrees. Okay, so let's summarize what we've done now. We've found the third vector, and we've done that using the vector sum, so f1, f2 plus f3 is equal to 0, or we found it by using the vector resolutes, so breaking it down into its x and its y components. When we solve a static problem, my main tip is to draw a diagram. And when we draw a diagram, we really need to be careful to make sure that our diagram is going from tail to head, tail to head, tail to head. So something like this, where we have a triangle, or sorry, our three forces which are going tail to head, tail to head, tail to head. Then we use the information that we have to find the length of the third vector, because the length of the third vector is going to be equivalent to the magnitude of the force. Lastly, we're going to find our angle using SOHCAHTOA sine or cosine rules, and we do that to find the direction of that particular force. Alright guys, so that's my video on statics. I will see you in the next one.